So in this video, we're going to dive into how we can use data beyond just predictive maintenance. We're going to explore how it can be leveraged to improve quality, increase throughput, and optimize your manufacturing processes. I'll walk you through practical real-world examples of where and how this technology can be applied. For instance, I'll showcase a bearing press machine where we use a specific machine learning model called an autoencoder to predict failures even before they happen, saving you time, money, and frustration. I'll also showcase how predictive AI is being used to improve throughput on a complex differential assembly line, proving that AI is not just about predictions, but actually making a tangible change on your shop floor. Along the way, we'll debunk some of the myths about prescriptive AI in manufacturing. And yes, it's complex to implement, and choosing the right partner is absolutely critical, but the results might just be worth it. Finally, I introduce you to Atlantis Foundries, a true lighthouse factory that has successfully implemented prescriptive AI and achieving a nearly zero defect on their production lines. This is a shining example of what's possible when you pair the right technology with the right expertise. If you're looking for ways to get results from AI on your shop floor, you're in the right place. Let's dive in. For the past 20 years, I've been in the trenches building production lines across the world. This channel is where I share my hands-on experience with anyone looking to make a real impact in their factories. Whether you're a plant executive, an engineer on the floor, or anyone eager to expand their knowledge on this transformative topic. Let's dive in. So welcome to part 2 of the practical use cases of AI on your shop floor. So in the previous video, I spoke about computer vision and those opportunities. Please go back and check that out if you haven't seen it. In this video, I'm going to talk about how we can use data more effectively on the shop floor. So I've divided up the use of data into predict and prescribe. So I'm going to start off with predict. So in this video, I'm going to get a little bit more theoretical on how the models actually work. So the first one, and probably the most simplest one to explain, is a forecasting model. So this is an example of where we would use previous data. In this case, it's vibration data from a particular machine. We would input that into a model, and we would then ask that model to forecast what does the future actually look like. And this is a pretty simple model to create. And from that, we can obviously trend what does the vibration profile look like into the future. And these forecasting models can be used for many different things. It could be used for sales. It could be used for production output. It could be used for A shift versus B shift. It doesn't really matter. Ultimately, what you're doing is you're using historical data to create a model to predict what does the future data look like, and obviously building a trend from that. I do want to spend a little bit more time on autoencoders and explaining more about autoencoders, because I think there's bigger opportunities using autoencoders on the shop floor. So the goal of an autoencoder is to compress the input data to as small as possible, but still represent the input. So you can think of it as like zipping or compressing down as small as possible. Yet when I want to unzip it, I'm able to get the data that I had originally. So an autoencoder, simply put, is basically taking a set of data, compressing that down through an encoder as much as possible to its smallest possible size, and then to be able to use a decoder and still reproduce the output as close as possible to the input. So to better explain this, I'm going to use the image of a cat. So imagine this brown cat is the input of the autoencoder. I want to train this autoencoder to the smallest possible compression to represent a cat. And that might be a couple of words that says pet, furry, 4 legs, whiskers, tail, not a dog. That is the small representation of a cat. And so the output after decoding might look like a cat, but it would have some differences. And if I compare the input X versus the output X, there's going to be a difference. In this case, it's color, maybe of the fur, color of the eyes, and that is what we call the error of the model. So it's comparing the input X to the output X, and the difference is actually what we would call the error. And we want to tune this autoencoder as much as possible to reduce that error as much as possible. And to do that, you put more and more data in on the input side, so you can do the encoding and decoding more accurately, so that we can reduce the error between the input and the output. So that I get to a point where if I put in another image of a cat, I get an acceptable output of a cat. And if it's not acceptable, I have to keep training the autoencoder to get a better representation of the cat. Say, for example, if I wanted color to be more accurate, I would have to add color into the encoder to make sure that I get the right color out. But in this case, I just want cat in, cat out. And where this becomes useful is, for example, if I input a dog into the autoencoder, I'm going to get something that looks a combination of a dog and a cat, which if I compare the input X versus the output X, is a huge error between the two, which is telling me that there's some sort of anomaly. Yet if I put a cat in, I get a cat out and the error is much less. So the idea here is that this is essentially an anomaly detector. So if I now input a dog and I compare input versus output, there's a much bigger difference between the input image and the output image, which is giving me some sort of anomaly. And I can set the threshold of error that I want to determine if it's an anomaly or not. So autoencoders in simple terms are good anomaly detectors, and this can be very useful. So let's dive into some examples. So this is an example of a bearing press machine that we've designed for one of our customers. And here's a short video clip of me actually using that machine. So as you can see, I load 2 sets of bearings into the machine, onto the tooling. I then take the housing of the differential, load it on, and I then press start. And the machine then goes in and presses in the 2 sets of bearings. And what happens is, to determine the quality of the pressing process, we monitor the force and displacement. And those force and displacement curves look a little bit like this. So typically you have this spike where the bearing touches the housing. It then settles down and then it gradually increases to a hard stop, which is where we push the bearing to the final position. And what we do is, to validate that the process is done correctly, we put these valuation windows in red to make sure that the press curve has actually gone through these windows. And only if the press curve has gone through those windows do we say that that part is actually okay. In some scenarios we get where you can see the press curve has gone out of those windows. We can then say that that is a not okay part, and we actually then fail that particular part. But what we found over time is that this transition from okay to not okay actually happens over time. And we've got no way of predicting when these failures are going to happen into the future. So what we did was, we then said, okay, could an autoencoder actually help us with this process? So what we did was, we then inputted these good press curves into an autoencoder and determined a good threshold and a good error. So we then tuned this autoencoder to recognize good press curves. And so we then built up this really useful autoencoder that represented these press curves on this particular machine. And to do that, we basically inputted 156 good curves, and what we got out of that was what you see in red is this reconstruction curve. And basically what we have is, the reconstruction represents the ideal curve of the process. What we were then able to do is use that autoencoder to determine which curves are now starting to deviate. So what you see over here in red is the reconstruction curve. So this actually represents the machine learning model, or the autoencoder model of the ideal press curve. And the blue line you see slightly behind it is the actual input from the machine of the force and displacement curve. And what we're then able to do is evaluate the area between the red and the blue curve. And that actually represents the error. So when you have a curve that comes into the autoencoder and there's a gap between the red curve and the blue curve, that area is what we would call the error. And we can determine the size of that error. And what we can then do is you have a look and see different curves and determine the area between the 2 graphs, and that determines the size of the error. So the next step in the process was to actually set up alarms and notifications. And to do that, what we did was we set a threshold. In other words, we wanted to set the maximum error or area between the 2 curves that would determine what an anomaly was. A really good indicator of the process trending in a particular direction, and allowed us to predict when we were going to start failing components continuously, and allowed us to actually take proactive precautions to prevent that from happening. Bearing in mind that these anomalies were not failed components, they were passed, but they were deviating from the nominal curve that we expected. This is an example of how an autoencoder was used to monitor the force displacement curve of a press-in process to help us predict when we were going to start having failures on the shop floor. This is another example of where we used an autoencoder. This is a very simple scenario where we have an oil filling machine, and all of these axles need to be filled in with a certain amount of oil. It's a pretty simple distribution of data, and as you can see in orange, the upper and lower limits. What happened was literally human error. So this process was pretty stable. A new variant was introduced onto the production line, and a process engineer adding the new settings for the new variant made a mistake, actually set the wrong target volumes for oil on all of the different axles. So not only did we fill the wrong volume, we actually set the wrong upper and lower limit. And so the system was actually passing all of the oil filling values despite them being incorrect. And the production line wasn't able to pick up this because obviously it was still within the upper and lower limit. Unfortunately, we didn't have an autoencoder, but in retrospect, we went and did this. We created an autoencoder for monitoring the stability of the oil filling process. And as you can see, once applying the autoencoder onto the data, we would have actually detected that there's been a sudden change in the oil filling values and created an alert. So for example, if we got 10 of these alerts in a row, we could have set up a notification to say there's something going horribly wrong here, there's been a big deviation. So this is a simple example of how autoencoders can add a second layer of quality assurance on shop floors and prevent that human errors in terms of setting up machines. This is another example where it's a measuring process. Again, the process is pretty stable. And what happened was there was a burr on this component and it bumped one of the sensors. And the sensor started to drift and obviously then started measuring the distances incorrectly. But because the tolerances were pretty big, and just to give you some context, the upper and lower limit is 50 microns. This measurement, even though it was drifting, was still within range. And so the machine wasn't failing the components. But these measurements were used in a process later down the line to actually determine different processes that must be performed. And a few hours later, when the wrong data was being used, the final production line started failing a lot of components and they couldn't figure out why, because all of the processes were still within range. Again, in retrospect, had we had an autoencoder in this place, we would have quickly picked up an anomaly. And again, if we had 10 anomalies in a row, set up a notification to say that there's been some drastic change in the process, we need to go and investigate what's going on before building hundreds of parts and then finding out that you've got a problem. So I think applying autoencoders on top of normal quality assurance processes using upper and lower limits is an extremely valuable additional quality layer to prevent either human errors or scenarios like this where you're not able to actually pick up the problem. So the last example I want to share with you on how machine learning can actually help is using models to monitor vibration data. So this is an example of a linear welder, and you see stuck into the bottom end of this machine is a vibration sensor where my mouse is, and this vibration sensor actually measures the vibration profile of this machine as it welds along this linear axis. Basically what we did was we monitored the vibration data and we were able to create a model and an algorithm that was actually able to determine different vibration states. And basically we're able to label those vibration states as on, off, and loading. So interestingly, the sensor was able to recognize the vibration pattern as the operator was loading components into the machine. And from that, we could actually output a lot of useful information. So we could create this cadence chart. So this is over a 24-hour period. So over here, you can see green is when the machine was running, yellow was when it was being loaded by the operator, and red was when it was actually idle, not working at all. And from that information, we were able to, over a longer period of time, over a month, we were able to measure utilization of the asset. So you can see red is off, green is on, yellow is loading, and black means the sensor was disconnected. And one thing we were able to do is from this little vibration sensor is actually count the number of cycles. So we were now able to get the productivity and production data from this classification model to the customers on their mobile phones as an example. And interestingly, one of the biggest opportunities we presented to the customer using this machine learning model and the vibration sensor was cycle time of the machine. So we were able to determine the loading time, the actual running time of the machine, as well as the idle time. And the customer was able to use this information to better optimize loading time and optimize the settings on the welding time to improve the output of the system. And again, this is using machine learning models to analyze vibration data, to not use it for predictive maintenance, but actually use it for productivity improvements as well. So that's an overview of how we can actually use data to predict outcomes on the shop floor. So the next section I'm going to dive into is actually prescriptive AI. In other words, how we can actually determine new settings for machines. So prescriptive AI. To help me explain, I'm going to use the example of a very simple injection molding machine. Obviously, an injection molding machine is some sort of control system. And in this case, I'm calling it a PLC. Typically, there is an output, normally a level of quality, a level of throughput, parts per hour, for example. And typically from the control system, we have a bunch of machine settings that are used to determine the process of injection molding. And then you could potentially output things like humidity, downtime, temperature, lots of data that is actually collected within the control system that can be used inside our prescriptive model. What happens is we then create an AI model. So we can call this the brain or a knowledge base, or in other words, this is the thing that's actually going to think based on the inputs that we give it. So the inputs would be obviously quality, throughput, machine settings, such as temperature, humidity, downtime. Could even put in operator working on the machine. So any input data that could determine an improved output should be fed into the model. You then train the model, in other words, teach the brain. And then what we want is, we want the model to predict optimized outputs to improve quality or throughput, as an example. So this is an example of prescriptive AI. Simply put, we have a bunch of input data. The brain determines new settings for the machine, and the machine ingests those settings and monitors the output data. And based on the output data, if it's improving or getting worse, the brain adapts and changes the settings again. So this becomes basically a feedback and a closed loop solution that is always adapting to the external environments to always improve for quality or throughput. So I just want to explain one example that we've attempted from a prescriptive AI perspective. It was done on a differential assembly line. Just to show you an example of a differential assembly line, it's a massive production line. So this is a production line coming together on our shop floor over a couple of months to assemble a differential like you see on the right-hand side. And there's many measurement processes, gauging processes on this production line. And ultimately what we're trying to do on a differential assembly line is to set the backlash of the two sets of gears. So the input gear, what we call the pinion, and the output gear, which is this ring gear. You don't want the gears to be too tight, it creates too much friction, and you don't want it to be too loose because then it creates too much play and can wear the gears out too much. Ultimately, what we want to do is to set the backlash. You can set the height of this pinion up and down, and you can set the position of the ring gear, let's say left and right. And to do that, we need to select a set of shims. And the shims would either go under the pinion to set the height of the pinion, also on the sides of the ring gear to set the position of the ring gear, all to try and set the backlash. And one of the key outputs of a differential assembly line is to select these shims to set the correct backlash. To do that, as I mentioned, we have a whole bunch of measurements that are denoted by the letters D, Y, P, etc. And we have a formula that we have that is used to determine S1, S2, which is shim 1, shim 2. And as in true engineering fashion, the formula doesn't actually work. And so we have to add in some offset factors. So we call that K1, K2. And what happens is on most differential lines around the world, it doesn't matter who the differential manufacturer is, there is always an offset required that is determined by a human. And so the supervisors with lots of experience are able to, using gut feel, determine what K1 and K2 should be. And typically the common first time through, in other words, differentials that go through the production line only once is about 70%, which is not good. And so most differential lines are designed with rework in mind so that these shims can be reworked effectively because the throughput is only 70%. And so this is a perfect case for trying a prescriptive model to actually help determine what K1, K2 should be. And this was done, it wasn't done by us, but done by a third-party company. They were able to ingest a whole bunch of data, create a prescriptive model, and they were able to predict the S1, S2 shims that improved the output to 80%. And this goes to show that even with a prescriptive model, don't get 100%. And basically what is needed is to actually ingest more and more data into the system to try and get the model more accurate. And I think this is a very important point, is that prescriptive AI is really hard to achieve on the shop floor. I think anyone that comes to you and pitches that prescriptive AI is a silver bullet for all of your problems on your shop floor, I would run away from them because it's extremely difficult to get the right data set, to train the right model, to output new settings for machines on your shop floor. So I would approach with caution. It's something that I would definitely recommend you experiment with, choose the right vendor, but it's an extremely difficult thing to get right. Having said that though, there is one lighthouse factory in my opinion with regards to prescriptive AI. And this is a foundry in Cape Town called Atlantis Foundries. And they have successfully adopted prescriptive AI to almost get to a point where they have zero defect through their manufacturing process. And these guys make big truck cylinder blocks. They've successfully adopted prescriptive AI on their shop floor, as I say, to get to almost zero defect. If you want to know more about what Atlantis Foundries have done, I actually had a fantastic conversation with Peter Duplessis, the CEO of Atlantis Foundries. It's on one of our podcasts. I'll share the link in the description below, and you can actually watch that.
And I also had the vendor that they used called Data Profit, that actually Atlantis Foundries, together with Data Profit, developed prescriptive models that got Atlantis Foundries to almost zero defect. The one thing that Atlantis did that was interesting was they still have the human in the loop. So the model predicts new settings, but the human still decides whether they put those settings in or not. They haven't actually completely closed the loop autonomously. They still get improved settings from the model that a human inputs into the machine. Really fantastic conversation. I would highly recommend watching. In the next video, I'll be talking about how we can use large language models and natural language processing to improve production lines. Stay tuned.